Hello, hello! Welcome to the stream. Yes. It's gonna be a good one today. Gotta get this sent out on Twitter. Gotta get the announcement out on YouTube, and we will be off to the races. Oh, what's this giant UPS on the bench? Oh, it's gonna be a fun stream. It's gonna be a fun stream. Hope you guys are having a great start, end, or middle of your day. But I hope it's great. Oh, looks like my mic's kinda... one sec. There we go. Got it kind of pointed the right way. Alright, look at that. Looks like we're getting some people dropping in. Excellent, excellent. Welcome. Welcome, everybody. So, you guys into inverters? You guys into power conversion? You guys excited to see what happens when we try to rip this microcontroller out of here and see if we can't, I don't want to say reverse engineer it. Hack sounds more appropriate, because we're basically taking the system that's meant to be there and replace it with something else. We're going to replace it with this great little dev kit down here. You might be wondering why we're hacking our own dev kit. Well, basically this processor isn't powerful enough. It doesn't have enough horsepower to do what we need it to do. There's a few different ecosystems, but I figured it'd be easier to port from Cypress to Cypress, and it, in fairness, was pretty easy, than it would be to port from Cypress to, like, TI. Now, it's not perfect, and quite frankly, it's untested. I saw that it kind of sort of looked like it was doing voltage regulation, but see, this board is made to feed 2 voltages to the micro, and this one's designed for the new UPS, which accepts 1 voltage, where kind of handles all the analog scaling and filtering for you. This is doing some of that in software. So I kind of had to hack it together. I'm like, just subtract the nominal DC bus voltage and divide by 2. So voltage regulation might not be so good when we hack this into there, but we'll see. We'll see. Alright. Got that sent out on Twitter. Man, that took a while. Maybe I need to learn how to type. But anyways, a couple other points in news. By the way, can you guys hear me all right? Can you guys hear the stream all right? I'm not seeing chat roll in, which is weird, because usually you guys say hello, but hopefully y'all are here. Anyways, we've got this little board. Let's see if I can. So we've got this little board, and it's a fun little thing. There we go. Basically what this is it will eventually be used to monitor the temperature of our lead acid batteries. You basically just put some thermal adhesive on the back, glue it to your battery, and then now you've got a remote temperature sensor. This is a nice big copper plane, so it keeps you nice and coupled, thermally coupled I mean. And this is a JST XH series connector. And what I've done is I've taken one of those and I've wired it into our dev kit. So we've got a 3-volt reference and a temperature probe, which this is using to actually run the ADC, since our old board runs at a different voltage, and that's critical because we're able to test a part of the new UPS. I mean a simple part, but still, it's a test. Get to test out one of our boards and have a little bit of fun. So as I mentioned, I'm not really sure if this is going to work. I have actually no idea. So I think what I want to do is I want to start by powering up the old UPS as is and just make sure that it still works. We haven't really touched this thing in months. So let's just make a sine wave. Let's test the transient response. Let's see where we're starting from. Frequency tolerance, that kind of stuff. We'll get this guy powered up and then switch over to the new controller. Alright, I gotta get some of this junk out of here. What kind of shop are you running here? Well, a messy one. Okay, so this should give us access to the controls. Gotta get the power cord. Yeah. Oh. Get the scope powered on. We'll be off in no time. Yes. It's gonna be awesome. Looks like it's gonna be a little tricky to see. Okay. Can I get that somewhere a little better? Maybe. I'll just read it to you. It's a pretty simple display. Well, so far no explosions. Not a whole lot of anything, but no explosions. I've had worse. Alright, let's check the picture-in-picture view. Let's see. Oh yeah, that's super not great. Alright, let's see if I can get that tuned. Sorry about all the lack of preparation. It's been a crazy week. Crazy good, I'd say. So wasn't able to test things out as much as I'd normally like to, but hey, that's okay. It's all good. It's all good things. Alright, so now I can see the scope. You can kind of still see what's going on over here. Hopefully if there's an explosion, you'll be able to see it. We'll switch back and forth between those two views. Alright. So, worth noting, there are a couple fans in here. You can probably see the one up top. This is blowing down. Actually, are you guys familiar? I'm not sure who we've got watching today, but are you guys familiar with this board, the Phase1 UPS? You guys know what this is? We built this a while back. If you got any questions, want to know what this is, just let me know. Basically, high level is, this is a UPS. This is built to take low voltage DC in this case. Well, maybe inverter is more accurate. This is more of an inverter than a UPS. But it was meant to be a UPS, there was just some issues with it. So basically this thing's made to take low voltage DC in, step it up to a few hundred volts, and then take that and make a sine wave out of it. It's pretty cool. Now, as a part of our testing, this is where it gets kind of weird, because the sine wave that comes out of this thing is actually floating. You might not realize that, but it's actually floating with respect to earth ground, which is pretty cool. So we can tie one of these legs to ground, either neutral or, well, line, and the other one, it basically, whichever one we tie to ground becomes neutral, and the other one becomes line. It's quite excellent. Oh, yes, by the way, I am forgetting something. I should probably unplug this while I'm wiring it in. I'm forgetting something, and that is, so I made a promise last week. I made a promise last week, and it was around these two boards. Last week on the stream, we assembled a couple of these EEforEveryone maker coins, 50mm round, and I promised that I would make sure that you guys could buy them somewhere this stream, and I did that. So there's an Etsy shop downstairs, oh my goodness, in the description. If you guys want one of these things, they're pretty cool. I'm not sure if I can ship them with the batteries, because lithium batteries, yeah, especially for you international folks. But it should be a worldwide store, should be open to everyone. Yeah. If you're looking around the store and you see more than just these maker coins, you might notice that, hey, some of these items seem pretty expensive for what they are. First of all, these are listed for way cheaper than I'm able to make them. I just saying thank you to you guys, letting you pick them up. If you guys really love them, what we can do is we can get some of these made from an assembler, and we can get them more like in bulk, make them, and make sure the cost gets down so I can sell them for, you know, $5. So anyways, these are listed for literally less than the components cost on the board. It's just a little way of saying thank you. But yeah, if you guys want to pick those up, check out the Etsy shop. They blink and flash, and they're kind of neat. We only got the two that we made in this stream. The incomplete one is, well, still incomplete, so yeah. If you're into flashing LEDs, check that out. We've only got the two, so they're gone when they're gone. But hopefully, if you were here for the stream, endured the 4.5 hours that it took to build these guys, get them working. Hopefully you can grab that little piece of goodness. Anyways, back to the matter at hand. Oh, wait, I didn't finish that thought. So you might notice that some of the prices are a little spendy. Like wow, that seems pretty expensive for a box of junk, or for a bare PCB. And a big part of that is, you know, if you guys feel like you want to contribute, if you guys like the cause that we're running for here and you want to support the channel, I want to give you a means to do that. and I'm not sure how to accept donations, so I just listed some stuff you can buy for way more than it's worth. So if you guys want to chip a buck in the hat and you want to contribute, buy those listings that make no sense to buy. You get some memorabilia, some thank yous, some fun pieces of our history, some boards you can build up and play around with some circuits that we designed. Which it's fun, right? It's meant to be like, support the channel and we'll give you a couple projects. So hey, if you're into that sort of thing, check it out. If you're not, no hard feelings. Just appreciate you guys watching. There's no obligation there or anything. Obviously, we're just here having a blast in the shop. Now, I am starting to get real nervous that my chat is broken. 15 minutes in, not one comment. Man, if you guys can hear me, if the stream's working, let me know. I want to talk to you guys. I want to say hi. Oh, wait a minute. I've got like a privacy setting. Oh my goodness. Oh no. What is happening? What? Oh boy. Yup. Oh, I see some chats. Good. Oh, thank goodness. I thought that it wasn't working. Hey Enzo, welcome. Oh, I saw like a privacy notification thing at the top that was like, you've got to tell us if this is made for kids. I was like, oh boy, did they just bury me? Hi Enzo, glad to have you. We're messing around with some sweet circuits today. One moment. I want to try to tell YouTube that this stream is not made for kids. It's not adult only. It's not made for kids. But for some reason it's not letting me get into my control room. Oh, I love this. I love how broken this is. Oh, alright. We might need to think about this for next week. Oh no! I can't see chat! What? Alright, I'm back. Hi, No Corp. On the phone. Okay, great. Thank goodness. Alright. Sweet. Alright, I'll keep moving. Anyways, welcome guys. I don't like the feeling of shouting into the void. I like it when we can talk and have a conversation, man. That's my favorite part of these streams. Alright, so what we got over here, alright, I need to prop this up with something so you can see it better. Whew, never mind all that nonsense. Here we go. So here's what we got. Yeah, you can't see that at all. What? Alright, here's what we got. Freeform. Basically, AC comes in, DC comes out into the UPS, comes in, all kinds of crazy nonsense happens, gets boosted up to around 300 volts over here, comes out to the inverter stage, gets chopped up, filtered, comes out through this terminal over here. This is where we're going to hook up our scope to line and neutral, and then that comes out to this connector where we can plug in some loads. That is basically what we're going to do. Cool. So in order to do that, to make neutral neutral and line line, I've got to hook up my just voltage sense to line, and then I've got to tie this guy to true proper earth ground. And there we go. The deed is done. So in theory now, if we come over to our picture-in-picture view and turn off the channels we aren't using, thinking about the waveform we're going to see, we're going to have 120 volts, so I need to make sure that we're in 10x probe mode. We are in 10x probe mode, and that the scope is set as such. 10x probe mode, yep, absolutely. And now let's get this set to a volts per division that makes sense. 50 volts per division, that means we should be able to see our sine wave just fine. Get our trigger level set. Make sure we're triggering on channel 1 rising, absolutely. Triggering on 50 volts should be great. And then the horizontal scale, what are we running? 60 hertz, pretty sure. So 10 milliseconds should be great. I'm gonna set that to single shot capture. Let's plug this thing in. By the way, Enzo, I think, and I'm trying to remember. It's getting harder to remember, but I think I still remember. You're pretty new to the channel, right? I thought I saw someone subscribe recently with a name that sounds an awful lot like that. Have you been here for months and months and I'm terrible, or are you pretty new? If you are pretty new, welcome, welcome. Happy to have you. Yeah, absolutely. It's great to have you here. Just a few folks hanging out in the shop and learning about electronics. If you have any questions, absolutely just let me know. I'd be happy to dive into more about what we're doing in our projects or what we're doing here today. Speaking of what we're doing here today, there's this tiny display that you probably can't read at all. Alright, I can read that on my screen. I'm not sure if that's going to make it through all the compression and nonsense that this has got to get through before it gets to you, but I can read that, so hopefully you can too. What we have here is voltage out, power out, voltage on the battery, which there's no battery installed, so it's 0. And if I grab the switch here, we can flip to another screen, and now we're seeing temperatures. This is the temperature at the inverter, temperature at the charger, temperature at the, I forget, I think it's the hotspot controller, and then the boost FET temperature, approximately. Flip to the next menu, and then we've got some statistics about the battery charger, which is kind of irrelevant, and then a couple different diagnostics here. So it's saying that our 2.5 volt rail is measuring at 2.5, that's great, and saying that our 27 volt rail is at 25.1. So basically those are the diagnostics that we have in here. What we're more interested in the voltage output and the power output. And basically what's going to happen is I'm going to click the start button, and now it's armed. And if I hit the start button again, we should see the scope capture, and we should see a nice soft start. Looks like I wasn't zoomed out far enough on the horizontal scale. But anyways, you can see we've got a nice sine wave. I mean, nice enough. There, let me rejigger that. We'll capture that again. I like the sound of this power supply revving up when you load it. Alright, single shot capture. Here's the readout from the display. When it's not running, it just shows you the old voltage. Oh, Enzo, discovered your channel looking for some info on power supplies. Sweet. Hope you found it. Hope you found what you were looking for. If not, let me know. I certainly do take requests. I can't always do them right away, but if you think you're missing something, yeah. And yeah, your English is great. Your English is perfect. Yeah, I'm glad you liked it. I'm glad you thought it was educational. Boom, there it is. There's that soft start I wanted to show you. That's supposed to be a linear ramp it's kind of more like dunk, dunk, dunk. You know, it's better than nothing. This is the old inverter control loop. This is basically we just ported it to the new micro. But yeah, so this is what we got. It'll just run. Let me grab a couple loads so we can, so I can show you some of my gripes with this thing. So to start, I'll go easy on us. Incandescent light bulb. It looks cycle by cycle. Nope, this is still old micro. Enzo. This question of the day. Yeah, so the new micro is laying down here with all the... I had this hooked up to my pocket scope with the signal generator and the 2-channel scope monitoring the PWM and force feeding it some control inputs to make sure the software kind of worked. But yeah, so the intention was always cycle by cycle. It just doesn't work very well. I hope to demonstrate that by dropping this load on, and we can look at the transient response. Okay. Oh, works better when you turn it on, huh? What? Is this light bulb burned out? You gotta be kidding me. Alright, I'm gonna go get a different light bulb. Hey look, a light bulb. There it is. That one turns on. Alright, so what I wanted to show you here is if we go into measure, do we have it here? No, we don't. Yes, it looks like we've got... It's not doing RMS? What? Come on. Gotta get that RMS goodness. Oh, you can't. Sorry, guys. It is intended to be cycle by cycle, but I think it's grouped into 3. It does 3 cycles and then it readjusts. Alright. Can we do a measure all? Oh, beautiful. I'm feeling lazy. I don't want to actually configure this. So we got RMS is 112, so it looks like we're a little under voltage right now. That's alright. But let's see if I can grab this. There it is. Alright. This is difficult to capture since it's an AC waveform. So what I'll do is I'll just try to have this free running for long enough so that we can kind of see the envelope. So here's the bulb. I'm going to click it on. See that nice dip? Oh my goodness, yeah. It's pretty slow. Pretty slow. So click on, click off, stop. There we go. Woo! Those inductors are getting nice and toasty. So that's one of my first complaints I want to bring up about this UPS. See, I blindly trusted a filter inductor datasheet, and they were like, yeah, this has got a current rating, don't worry about it. Oh yeah, I bet that light bulb is quite warm. And so they didn't give like a frequency derating curve for how much current this thing can handle. These inductors cannot handle the kind of these are made for like AC line filtering, not for a couple hundred kilohertz. Well, yeah, so right now, basically when there's no RMS current flowing out of the UPS, there's enough high frequency current that these things get hotter than the surface of the sun. It just from filtering. I mean, I know there's real current flowing, but like, that's supposed to be when it's easy. And I think it's just core losses. Maybe it's winding too. I don't know. It's hot though. So yeah, in the next version of this, we're winding our own inductors. I designed my own because I didn't want to have to trust data sheets. So it was like, we're just gonna build ourselves a nice high frequency inductor that it's not too hard. I'd rather do that and have it work. But so for a concept of how much current we're pulling, this is a 60 watt bulb, so we should be pulling half an amp. And when we grab half an amp off, the transient that we saw was a minimum of, yikes, looks like that transient was, what, 68 volts, really? Dang, that's like half our output voltage. Oh my goodness. I mean, it's probably fine because stuff that's hooked up to mains is designed to ride through dips and interrupts. So like when you're plugging something in, it's fine if you dip like this, but oh my goodness, that's a lot. The bigger concern for me would be when we're going the other way, it's not quite as bad, but we've got a voltage peak of like 50 volts. Our 120 volt AC output gets up to, what is that, 230? Yikes! That's a pretty high voltage. Yeah. The metal file? Is that my terrible joke? You liked my terrible joke in the video this morning? I had some fun with that. I was just messing around a little. Yeah, just like, I don't know, just having some fun. So yeah, there's a couple reasons why this happens. First of all, the control loop's a little slow. But the second reason why is because we're not even able to run the control loop at the designated frequency. Like, it was designed to run at an interval of 1 millisecond, but the poor little PSoC 4 we've got running the control loop is like, help! I can't do math that fast. So, yeah, it can't do math that fast. So, man, I'm really trying to stall because I've got a feeling everything's going to get a lot less pretty once we switch this micro over, but I don't think I can stall anymore. I think it's time. So what I've got to do that is I've got my pin mapping for the PSoC 6 project, and then I've got the old inverter design. I double checked my firmware. There's really no error handling between these two micros. It was always on my radar, but the power electronics didn't work well enough, so I never went around and finished the software, which is fine because we've got some big changes now, and it's all gonna kind of work itself out. But basically what that means is really good because we just want to kind of throw this new micro in there, and I didn't have time to finish like all of the software, so the voltage readout won't work anymore. The temperature probes that are monitored by the inverter micro won't get over. You good? It's fine. You chuckled. It's all good. Yeah, cool. I'm glad. So like a lot of the diagnostics and monitoring just aren't going to work anymore, but I never introduced the fault handling routines that'll rip the power cord out, because basically either of these micros can disable any of the power circuitry as a safety feature. So if one of the micros goes out to lunch and we start applying 500 volts DC to our AC load, it'll just be like, nope, and it'll resolve that fault really quickly. Like, they're constantly in sync. And basically, when they fall out of sync, I just don't do anything. instead of, you know, resetting the micro and reinitializing and all that. I just never got around to that. It's worth noting, I do have this chassis tied to earth ground through this anemic wire. I should really get better ground wire, but it's better than nothing. So this whole high voltage region is isolated. It's at 250 volts DC nominally, and then it gets spat out on the inverter. Yeah. So Nocorp, you did oh my goodness, make a really great point on that the current rating is when it melts. Yep, like the DC current rating. Absolutely. I'm not sure if that's what I'm running into here, because these are some pretty beefy inductors. They are, well, I don't have the part number on me, but I think they're 10 amp rated, 250 microhenry inductors. And so when we're passing like an amp through them, and then they start to get hot enough that you smell it, it just didn't feel right to me. I dug into it more. They're definitely made for like line frequency filter applications, not for 200 kilohertz switching applications. But that's okay. In general, this whole front end's getting revamped. I mean, I think we talked about it a few months ago, which is crazy that it was a few months ago, like the new inverter designs. But yeah, it's all coming, and it is good stuff. It is good stuff. Okay. I filibustered as long as I can. It's out. Micro's out. Oh man. Alright, I want to see if I can't get this a little more in the frame for you guys. There it is. Oh boy, pushing on things that aren't screwed down. Hurt. Click. Yep. There it is. Sweet. So now you guys can kind of follow along as we're working here. This is where it's going to get a little interesting. Got our pin out for the new micro. We've got the pin out for the old micro. Now I've just got to link some critical signals from one to the other. We will be good to go. Voltage reference is standalone, which is very helpful. Okay, these are the two PWM outputs. That's easy. So that goes to 0.3, 0.4. Oh boy, it's gonna be trickier than I thought. Okay, so now I've got to kind of look at this. These are complementary PWM outputs, so they're always 180 degrees out of phase. That's very helpful for us, because that means we just need to spit out sinusoidal PWM signal, and then one of our half H's is always the opposite of each other, so we basically set both of them to VCC over 2, then modulate from there. Right, that's 3 and 4. Yep, you got the PWM hooked up. Alright, got a couple comments here. The joke was more that typically it's like current rating is when the wires. Yeah. Yeah, that's fair. When the wires are at 120 degrees and rated for 150, or with semiconductors junction at 175. Wait, you mean You don't run your semiconductor devices at TJ Maxx all the time? What? Oh, I've been doing it. No, I'm joking. I'm joking. Yeah, definitely. Might work for 1,000 hours. Might. Yeah. Might be a good idea to keep the electrolytic caps away from heat. Oh, yeah. Oh, yeah. I don't think we got a lot of electrolytic caps. Like, this side of the board gets pretty cool. Oh, you mean the ones right next to those giant heat sinks? That's a fair thought. These are some big old film caps that are right next to a transformer. Well, big. They're like 7 microfarads, which is a pretty small cap, but when you charge them with 250 volts, there's some energy there. There is some energy there. What else do we got? What else do we got? So I think that's actually all I gotta wire in from this harness. Oh, no, ground is gonna be important. Ground is connected. And then we need the inverter enable. The UART is not used. So, inverter enable. Where are we? What's my name? Who am I? Inverter enable in 0.6. There it is. There it is. Got her connected. No problem. White. What was that connected to? That was connected back to 6.3. What is 6.3 in our new pin mapping? That's inverter enable out. So that's what actually enables the inverter. Yeah, we should probably, or the boost rather. We should probably connect that. Like, maybe. Maybe. Where does that need to go? We need to do boost, enable, out, and in. Yeah. So that'd be 4.0. So we want 4.0 and 4.3 to go together. I didn't think about that. We need to tie this signal to 2 nets. 4.3. And if this works, I'm gonna be shocked. 4.3. Yep. Yeah. Yeah, that's a good point. That's a good point. The electrolytic cap. Sorry, I was just reading chat again. You guys having a good day so far? You guys enjoying life? Let's see. Let's see what I've got to make a Y cable here. Not a whole lot. I've got a breadboard. Yeah. Let's get a little creative, shall we? So what I'm gonna do, I'm just gonna grab one of these little wires. I'm gonna poke that into the 4.0 pin, which should enable the other inverter. Yeah, Looks good to me. Yeah, hopefully not literally shocked. Could not agree more. And then what I'm going to do is I'm going to take one of these little test clips, and I'm just going to use this to bridge the signal from one pin over to the other. Just going to hook it. So there we go. Great. We've got that jumpered over. As long as I'm vertical, everything will be just fine. Now, JD, I don't mind being a horizontal as long as it's only temporary. A little bit of horizontal time, and that's good for me. Sleep is good. But I get what you mean. As long as you're here, you're good. Couldn't agree more. Alright. And so, I believe I've Oh, this is kind of funny. So I've overridden the overcurrent protection in our control loop, so it's pretty much just gonna not care. Horizontal and underground doesn't sound like a good time. That's awesome. Oh, what was I saying? What was it? Oh man, that totally distracted me. In a good way. In a good way. Oh yeah, so we totally overrode the overcurrent protection on this thing. It just doesn't care. So we just feed it a voltage, and it's just gonna try to pound some voltage out of this UPS, and if something explodes, it explodes. So that's pretty fun. So all I need to hook up is one of the voltage monitor pins. So this is kind of where, let's see if I can show you this. I think that's in focus. So this is kind of where that weirdness comes in, where there's two pins that bring voltage feedback to the micro. It's actually like a oh no. Oh, that's a differential ADC output. Should be fine. I think I compensated it wrong, so our voltage is going to be wrong. But it should still make a sine wave, hopefully. Oh boy. Read your schematic. Yeah. We'll see. It'll do something, that's for sure. So I'm basically just gonna hook up to one of those outputs. So it'll be biased to VCC over 2. And then, yikes. Alright. So let's try VO mon negative, which is coming into pin 2.7. There it is. I might just need to count this one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There it is. And this guy came out, which was 4.0, 4.1, 4.2, 4.3. Yikes. Things are falling. In theory, it should work. Just gotta break the insulation on this guy. I can hook the probe in there. There it is. 3. Four 4.1, 4.2, 4.3. All right, what do you guys think? Oh, yeah, 2.7. Yep. Yep, that's how this is organized. So the way they number their pins on the Cypress parts is bank.pin number. So, yeah, I mean, like it on the port and pin number. I wasn't actually listing micro pin numbers. So it's like, well, one of these is a BGA, the other one's a quad flat pack. But I just broken out on their dev kit, they've got the port and pin labels. Yeah. So, I mean, just want to like turn it on and see what happens. That's kind of what I'm feeling. Like, I don't know what's gonna happen, but it should at least be interesting. Yeah, I am. Yep. In fact, you can call that wired. So we've got jumpers coming from the new micro, replacing where that old micro used to be. So we're tapping off the analog voltage feedback that comes into our control loop. We're feeding it PWM generated by the new micro, and the logic interface, which is like the enables and whatnot. We haven't hooked up all the diagnostic, all the UART, and implemented that protocol because time, mostly. But this should be a pretty independent, ready to rock and roll implementation. The only problem right now is that we've got this thing set on a giant sheet of metal, and we need it to not short itself out against the chassis. Hey, look at that little bag. That, sure, why not? We'll call that good. Who wants to fire this thing on? I know I do. Oh, I know I do. We're gonna try it unloaded first, just to see what happens. Who knows? Oh wait, we gotta power on the micro. Since this is running off a dev kit, I've actually gotta feed it power through a USB connector. Gotta somehow fish this guy in there. Carefully. No sudden movements. Should have done this first. There it is. Yep. Super great. No problem. Oh, I gotta find a power brick. Hey, look, a power brick. I suppose I could run that straight back to my PC, but I'm not feeling that. Not feeling that lucky today. All right. Micro is powered on. Okay. It's on. Let's take a look at our diagnostics. Let's see what we get. No voltage, naturally. It's off. Come on, where's my buttons? Where's my control panel? There it is. So now you notice some of our temperatures are no longer present. They're just reading 0 because, you know, there's no feedback. So basically anything under inverter control, we can't monitor anymore. I think there's only one thing to do. Three, two, one, cross your fingers and hope. I might even plug my ears for this one, man. This might be loud. Primed. Dang it! Why not? Why not? Did I miss by a pin? Just noticed our fans aren't running. It's not great. There we go. What? Alright, whatever. Just need to make sure that the main one's going more than anything. Okay. What do we do? What do we do? There's a lot of things that could be wrong. There are a lot of things that could be wrong. Where do we want to start? Let's start by monitoring this enable waveform. Because if we never enable the high voltage stuff, it's never going to turn on. So when 4-3 is set to a logic 1 and an inverter enable is set to a logic 1, we would expect oh, wait a minute. Inverter enable needs to be, oh, wait. This is inverted. When this is pulled to a logic 1, when inverter enable out is set to a logic 1, it's pulling inverter enable down. Oh, that should be good. Yep. So it's undisabling the full H, and at the same time, we're enabling the other supply. Okay. Thought I found it. Nope. Okay. Where can we position this? Can you guys? Looks like you can see that. Yeah. Debug time. There you go. So, got to set to DC volts. Ground. Let's check that enable pin. Enable pin, we are disabled, which makes sense. This should be disabled. Did I ever write the logic to actually enable this pin? I don't know if I ever wrote the logic to enable that pin. These should both be at, oh no, bent the pin. These should both be at VCC over 2. Yep, those are both at VCC over 2. PWM's coming in. Analog voltage feedback is hopefully right around 0 volts. Alright. Let's hit this with an enable. And then an enable. enable. Let's check the signals again. Ah! Yes, looks like we're not actually rating the enable pin high. Well, that'll do it. But now, hopefully, these look a little different. Alright, this is going to get a little weird. This is just a thought. Oh. There it is. 1.6. 1.6. Yeah, so we need to write some logic that'll kick that on. Or we can just tap the enable over from the micro. It should all happen simultaneously. This will just make it happen very simultaneously. Yep. So all we've got to do is tap our enable over. Easy. So we're basically just removing control of the enable from the inverter itself, and when the master controller enables the inverter, we'll make that enable the downstream circuitry as well. The main reason why is just because doing firmware updates for this would involve me needing to run over to a different system, like a different computer, work on software for a while, and then come back, and that just doesn't seem right. That doesn't feel right to me. So I'm gonna see if we can't do this with hacks, bubblegum, and baling twine, so that we don't need to like pause for 30 minutes for me to go do firmware updates. By the way, I don't know if these went yet, but these are up for grabs on the Etsy store. I'm selling them for way less than I put into them to say thank you. So if you were here for the stream and you want one of these things, yeah, it's a cool little piece of memorabilia, and I really want you guys to have it. So enabled that on the Etsy shop if you weren't here for the start of that announcement. Alright. Another one of those little clips. White sounds good. Now this could go bad in about 15 different ways. There's a very important reason why I have the inverter microcontroller enabling the downstream circuitry. And when we bypass that, there's a lot of reasons why that makes me nervous. Like, we start a soft start routine when we enable it. So basically, we're just going to be spitting out blind PWM for like few, I don't know, seconds? Milliseconds? However long it takes the inverter to kick on. That's not determined. Makes me nervous. Alright, let's blow this thing up. Try number 2. Alright. I might need some encouragement, guys. I might need some encouragement. This UPS is expensive and near and dear to my heart, and I might be about to blow it up. Just blow it up. Alright, sip of coffee for courage. I think I can do it. Inverter micros turned on. Let's go. Okay. All right, JD. Hit me with a go, and I'll push the button. It's armed. All I gotta do is hit this button again. Yeah. Oh man. All right. It didn't seem to go. That's really weird. Man, I'm sweaty. I'm like sweaty palms right now, man. 250 volts is flying around, and I've got a breadboard and a bunch of loose wires in there. What could possibly go wrong? All right. Alright, that seems weird. Got 1.6 volts on the enable pin now. Something's fighting. Something's fighting. We're not able to fully assert enable. Why aren't we able to fully assert enable? Maybe I've got one of these pins tied wrong? If we're hooked up to 4.3, we should have a 5K resistor. Inverter, enable out, 4, goes to another 5K resistor. Weird. Two micros fighting. Where's the pinout? Here it is. Did I hook up the wrong one? We've got gray wire going down to 5.2. 5.2 should be master enable in. That's an input. Okay. Let's try this again. That's pretty weird. What I'm going to do is I'm going to take advantage of this standoff. This is actually why I installed this standoff. Gonna clip on the multimeter probe, and then we're just gonna hook this guy right into that enable signal with yet another one of those clips. I want to be able to monitor that net. It could be a micro fight. I really think it could be a micro fight. 2 pins fighting for dominance. Alright, this clip is super bent. Annoying. Alright. I really need to get some of those Pomona mini grabbers. Okay. Okay. So now we can monitor the voltage. Whoa. I've got 1.5 volts now. That's not right. Why do we have 1.5 volts? I rebooted the downstream micro. We no longer have 1.5 volts. I think we might have just needed to reboot the micro. So now we're seeing 68 millivolts. That seems right. Hey. Let's see what happens. Goodness. Okay. Yep. All right. I think it's a micro fight. All right, 50 millivolts on the enable. Oh, this time's the time. I'm feeling it. I'm feeling it. Click 1. Primed. Click 2. Why? Why 1.6? I'm so mad. I'm so mad. Alright, let's just get our micro here. I'm going to disable this downstream circuit. So now we're seeing 1.5 volts. Reboot the micro. Looks fine. Power cord plugged in. Click on. Click on. There's 3.6 volts. Why? Why when I attach this downstream circuit does it get angry with me? Okay. Let's check it out. We're at basically nothing. This is bizarre. And we've got nothing on the output. What? The output's working. There's 3.3 volts on the output. That logic was working. What? Okay. I'm going to try disabling. And it turns off. Okay, so our code was working. It enables and it propagates through. But when we actually hook it up to the downstream circuit, I think we're off by a pin. That's my explanation. I think we're off by a pin. Yeah, the oscope is hooked up. Yeah, so that's the problem, JD. It should be going, and it's not. The oscope is showing the output voltage on the inverter, but since we're not asserting the enable, it's doing everything else. It's just not actually enabling the circuit. The most frustrating error. Is 0. The weird thing is that should be going to a couple open collector comparators. It's bizarre. I'll give it another ground reference. Maybe that'll help. Better tie the grounds together. That usually helps. Yeah, and we've got, I'm going to count these pins out. So we want to connect that to inverter enable out, which will be pin 4. Counting down, that'll be 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Pins down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That one's correct. 12, 13, 14 for 4.3. That is correct. So we're connected to the correct pins. And yet, somehow, it doesn't want to go. let's check that again. Let's monitor the enable signal with one of the two enables. So we're going to only enable, the inverter, not the boost. And let's see if we see the weird voltage state. Should just be an open collector comparator for some reason. Or sorry, an open collector NPN. But we're seeing something a little weirder. Right, seeing 0 volts on the enable, as we should. Click enable once. Primed. Click enable twice. Seeing 3.3 volts come out on that enable. Great. Now, if we connect the second enable, click it once to turn it on. Click it the second time to arm. 3.3 volts on the enable. Alright, why aren't we on then? This looks like our enables are working now. That's good. It's very good. Okay. So that's sine. Micro is still running. Let's double check our PWM inputs. That's kind of important. So we should be running at 1, 2, 3, 4, 5, 6, the 6th pin from the bottom. We are on the 1, 2, 3, 4, 5, 6th, and 7th pins from the bottom. Just come back to 8, 2, and 8, 3. That looks right. Yep. Man, I might be at a loss for this one. So we have the PWM coming back on the board correctly. The only other thing I can think would be if our analog feedback, if the DC offset is throwing us off. And I can fix that by tying our analog feedback hard to ground. So no matter what the control loop's doing, it should definitely give us a sine wave now. Oh, actually, that wasn't the problem. That wasn't the problem. Because we should still hear the PWM switching action. It's like loud. So that was on the 1, 2, 3, 4, 5, 6, 7, 8. 8th pin. Whew. Okay. Let's check the inverter enable again. Okay. There's one other thing that could be happening. The inverter E-stop could be... Alright, you guys got any thoughts? Oh, I guess... Oh, I didn't release this schematic because UPS, risk, ethics. Oh. Alright. Makes it harder. Makes it harder. So basically what we've just confirmed is we've confirmed that the PWM signals are getting on the board. The enable is coming off. And the enables are enabling the downstream circuitry. We have confirmed that all the inputs and outputs to our board are doing what they should be. That's kind of tricky. Yeah. Yeah, that's pretty weird. So, what now? What now? What to check? What to check? I'm perplexed. Micro's still running, still doing its dance. But these supplies are not turning on. It's either the boost or the gate driver is not turning on. I'm gonna guess it's the boost. Let's dig more into that. Because if we don't have the high voltage, nothing else happens. Alright, so we've got the boost schematic here. So, alright, what happens? When boost disable is asserted high, this transistor turns on. Turns on that transistor, clamps this compensation pin off. So when this is a logic 1, that is off. This comes out of that page as boost disable. Where'd my okay. So when boost disable is a logic 1, we turn off the boost. Boost enable is normally tied to the power input, so it is normally disabled, and when we pull it to ground, it should be on. So when does boost enable get pulled to ground? Boost enable gets pulled to ground when we assert pin 4-3 to a logic 1 state. Well, I guess that's where we probe next, huh? Let's probe the high voltage bus, see if it's turning on. Alright. We're officially in don't try this at home territory. Alright. So, DC link, I gotta double check where I need to probe here. So basically we need, oh, that ain't right. D8 cathode, is that accessible? No, it's kind of buried in there. But we do have that regulator body, so we've got a good negative terminal. C91. Is that helpful? No, we need C10, C11. Those are kind of buried. D22. It's on the inverter page. D22 cathode. There it is. Alright, found our probe locations. Alright, we got it. Let's kick it on. I don't really know where to leave that. Actually, let's turn that off for a moment. So I want to observe one very practical piece of advice. The critical thing is that high voltage is quite dangerous, in fact. 0 out of 10, don't mess with it. And high voltage DC is even more dangerous than the rest of it. And so it would be a pretty bad idea for me to hold both scope probe clips and just kind of hang out. That would be a very bad idea. So what I've just done is I've automated holding one of those clips. And I will keep one hand on the other probe. Check out this high voltage DC bus. 13 volts. Yup. So that seems to be why the inverter is not on. It's not a whole lot of volts. Okay. That's pretty benign. 13 volts, eh? Looks like something about that enable signal isn't getting back to where it needs to. Goodness. Alright. So we're asserting enable that pin, and it goes to Q12. Q12 is right over there. Q12 pin 1 should be the base. What? Oh, there it is. Q12 pin 3. Whoa, whoa. So there it is. Something's not right. Q12 pin 3. There's no power getting over to this controller. It's the reference pin. A reference pin doesn't have any voltage on it. That's pretty weird. Oh, there it is. Q13 pin 1. Is that up to ref? Okay. That's right. Pin 2. Yep, also hooked up to the reference. Pin 3. Alright, let's kick this thing on. What do we see on Q12 now? Alright, 0.7 volts on pin 1. Wait. I see 0.7 volts on boost disable. I think I might have my logic state reversed. So I think that we disable the high voltage rail when we enable the inverter. I thought I just traced out this logic. But based on those transistors, telling me I was wrong. I'll check it again, no worries. I'll check it again. Nothing. Something ain't right. Because we saw this thing change state. The enable pin went from a logic 0 to a logic 1, but we're not making the high voltage. All right, I've gotta swap in the old micro again because this thing is not doing what it should. I just want to see if the board still works. I want to see if we blew it up. Because it's like, we traced out the enable signal. It seems to be enabling when it should, and disabling when it should. So that's all excellent. I've seen the control loop work, but it's just not bringing up the high voltage rail. So what I'm going to do is I'm going to probe the nuts that I thought we were connected to and just see what happens. All right. Plug it in. Alright, sorry, forgot to take my, there we go. Okay, so now coming back to the low voltage side of things, I want to check the states of a couple of these different pins. Then I guess check all the pins and logic states. Oh yeah. Yep. So what I would expect to see in the off state would be exactly what we just did. I would expect to see pin 4-3 and 4-0 as a logic 0. There's, I'll get the micro in there so you can live it with me. Yeah, that is completely illegible. Sweet. Here it is. So we're checking 4-0 first. To logic 0. 4-3. Logic 0. Good. The enable. Coming in should be 0.6. Should be logic 0. Great. I'd expect to see our outputs at VCC over 2. So that is 3 and 0.4. Yep. VCC over 2. I did check the logic input level, because this is running on 5-volt logic, the other one's running on 3.3. I made sure we weren't going to blow anything up when we push the two dev kits together, and that the logic level would still be valid. It absolutely most certainly is. Because we're driving BJTs, so as long as there's enough gate drive, we're good. So now we kick the inverter on. And now we should see 4-3, logic level 1, 4-0, logic level 1. And now these are going to be doing a little something crazier. Those are going to be doing AC. Which if I switch this over to AC, just curious what the amplitude is. 2.9 volts AC. Dang, that's almost full scale. Interesting. Anyways. And then the VO mon coming back. It's also going to be AC. 2.7. So we're getting 0.13 volts AC with a 1.1 volt DC offset. Okay. So I'm pretty confused. I am right and proper confused. Because the difference between what we just did and what we did before is we're driving a BJT with 3.3 volts instead of 5. Yep, and that's it. I don't even. Well, good to know the board still works. I'm confused. Yep, there's a base limiting resistor. I'd have to pull up the drive analysis to answer that. But realistically, these are 3904s. They should have a gain of around 40 at where we're running. Let's do a little bit of mental math here. So if we're driving 3904, let's say the gain's 20. Let's be a little conservative. That's pulling down a 10K resistor. So we need 10K 5 volts. So we need half a milliamp. Divide that by 20. We need not very much current. Alright, take that and 3.3 minus 0.7, that's how much voltage we're putting across our resistor. Divide that by 5.76K. We have about inverse. We've got 18 times more base drive than we need. Yeah. Should be okay. So we've got a 5.76K resistor on a 3904 BJT pulling down on a 10K resistor. So we should have plenty there. Let's make sure the boost enable's got this same margin. No, that's a good point, right? We checked the logic and the logic's right. So either I was off by a pin or it's the drive. So now we're pulling down on, oh my goodness, even like we've got cascaded gain here. So on this one, we're pulling down on a, oh wait a minute. We're pulling down on something much higher here. We're pulling down on 12 volts through a 50K resistor. Let's check that. Let's check that math. So we got 12 volts through a 50K resistor. Oh, that one might be close. Oh, that one might be close. Oh, we might be onto it. No corp, you might have nailed it right on the head. The boost enable to pull that 12 volt through the 50K resistor, that means we'll need 0.24 milliamps of current to enable that converter. And what we've got on the base drive side of things is the same 3.3 minus 0.7 divided by divided by the same 5.76K. So we still got a ratio of 2. That should be enough because our gain should be around 40. So we should still have some margin. Oh, I think we just wire it up again and hope that I missed. Because that really should just kick off. Double checked our logic. Double checked everything. So hopefully I just missed a wire and throw it back in there and we're good to go. Double check the saturation, but like if I were designing this fresh, I would probably want more margin than that. But you know, that'll be alright. She'll be right. Alright, so we need, yeah, this is the voltage monitor. Come back to the ADC. What's that looking like? Voltage monitor coming back on the ADC. 1, 2, 3, 4, 5, 6, 7, 8. 8th pin. And ground. Perfection. That's all we need there. Going over to the rest of our control signals. Get the master enable in. Coming in on 0.6, that's the fourth pin from the bottom. 2, 3, 4. PWM outputs. These two. Give that a nice ground reference. PWM L1, L2. That should be connected to point 3 and 4. So that's 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. Those two are adjacent. Plug that in. Then we've just got the enable out, which should be going to 4.3. 4.0. Let's count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here's hoping. Here's hoping. And then from there, we should go down 1, 2, 3. 1, 2, 3. And there should be 2 LEDs. R170 goes to red LED out, so I'm going to sneak in between the 2 pins. Oh, gotcha. Gotcha. Yeah, that looks right. Should be. I love that comment, Norcorp. Should be saturating. Yes, should be. Should be. Alright. Of course, forgot to turn the thing on. There she is. Powered on like a champ. There goes the rest of the board. Let's check some of our signals, eh? So we should see 0 volts here. Got it. We should see 0 volts here. Got it. Let's check that boost enable signal. Coming in. R14. Where's R14? R14. No? None for me? Okay. Let's try this one. Boost enable in. R35. R36. There they are. 35, we're seeing. Alright, yep. We are definitely turning on that disable FET. Or disable BGT. My goodness. English. English. Alright, so we're getting 2.7 volts applied to what's R36, the pull down? Yes, we got 0.7 volts. 0.7 volts on that BJT. We are super good. In the clear. Now let's try kicking this on. Let's see what happens. We pulled it low. It's 40 millivolts now. Why aren't you on? UPS! Why? Alright. We turned you on. Why aren't you on? I saw the enable pin change state. I observed it like at the control signal. Oh my goodness. Alright, my mind's blowing. Okay, so we're changing the state of that. Let's check the DC bus now. Maybe the high voltage DC bus is working now? And if the high voltage DC bus isn't working now, I'm so confused. Because we're enabling it. There's nothing else required to enable the bus except for enabling it. There we go, 320 volts DC. Hey, that's a step. Alright, so our DC bus is being enabled. Nailed it. So it must just be the H's. All we gotta do is enable the H's. Looks like we've discharged the bus down to 0. Hey, that's good. Guys, we made progress. We made progress. Let's check our other enable signal. Okay, the other enable signal says oh my goodness. Now we're just on this schematic page. So we're looking at the inverter enable in, which is R173. R173. We're getting 5 volts on it, which is disable. Our which side do we want? Our 173 is connected to pin 2, 3, 4, 5. Pin 5 of the micro, that is the disable side. Alright. So, wait, what? Why is that disabled? Then we kick it on. What? We're disabling the H's when we turn on. Okay. Alright, this is gonna be weird. I'ma just okay. So it looks like if I just do this, it should just come to life. I think it'll just come to life, guys. Still with me? Still with me? Still here? Cause this might be the go. This might be the go. Single shot capture. Hey, tested. So this is the Phase1 UPS. We're trying to bodge on my new DSP, the PSoC 6 DSP, hook it into the old dev kit, and see if we can get some voltage out. We confirmed it's enabling the 300 volt DC bus, and we're gonna see if we can get it to make a sine wave. Ain't no time like the present. Really? Really? Gonna be like that? Okay. Alright, so I think what it comes down to, if you guys have a computer with you, if you guys could look at the SI8231 and just check what the logic state and valid logic input level is for the PWM input. Because we're feeding it 3.3 logic on the PWM signal. Just want to make sure that that's good. Just want to make sure that's good. Could be as simple as that. Because we're getting PWM back there. Both of them have it, yep. And what's test point 1? Converter enable not. So it looks like right now it's enabled. $2 volts. Yeah. What the heck? So we're feeding it the high voltage. We're feeding it the PWM. Why? What? Why? That's all I want to know. I mean, it's gotta be. That's all it could be. Because everything else is exactly identical. So I should just drive an LED. Or not. Alright, let's get a logic shifter, because it could be UVLO, but that should be exactly the same. I thought disable. I've got the net labeled as inverter enable not. That's what the net's called, and the pin is called disable. So I think it's active low, like when it's pulled low, it'll make PWM happen. That's my understanding. And we got a 12 volt hot input. I'm just gonna double check I don't need to switch that on, because I've got a voltage boost isolator thing. It's getting power across the boundary. Feeding it VDD, but I can't see where VDD comes from. Oh, it comes from power entry, which conveniently I don't have. Let me go grab that schematic sheet. Got her? Oh, yeah, it's just always tied on. Basically, we're just tapping off the 7 volt, regulating down, and boosting it up to unregulated 15 volts. Datasheet has active high. When brought high, the disable in... Okay. Okay, so... When brought high, the disable input unconditionally drives VOA and VOB low. Okay, so we want... When we want the inverter to be on, we want that input to be 0 volts. That's what you're telling me? So it looks like we're turning it off. Inverter enable out. So when that, okay, I might be stupid here. I'm feeling pretty stupid here. So we've got this pin, which is tied to that. So we want to pull it low. Wait a minute, I know what this could be. I know what this could be. Because... Oh, I think I know what it is. Because this micro is holding it off. Yeah, it's basically enabling that until it... Okay. So we're gonna look at R174. Sorry guys, I'm thinking. I'm so bad at talking while I'm thinking. 174 should be coming straight back from our micro. And hopefully we'll see that tick to a logic 1. We do not. Alright, why doesn't it? Are we off by a pin? Let's find out. $174. Let's trace that guy back. And 74 should be coming straight back to our micro. What? What? I'm sorry, what? It has to. Alright, well I think I found the problem. Yeah, we could. Yeah, the problem test is that this thing does like a soft start routine. So if we permanently latch that guy on, it might blow up our FETs, because it powers on in a very intentional sequence. It might shoot through if we don't power it on right. That's tricky. Yeah. So that should be just on inverter enable out. Pin 4.0 should go straight to R174. Why doesn't it? I got this in ohm mode. Just gonna quick make sure we're getting good contact. Whoa now. There we go. Getting good contact. Hopefully we'll see that it connects. Okay, there it is. That's our pin. That's our guy. Right there. And now, what I want to see is I want to see that pin change state. Nothing so far. What? 3.295. Probe the resistor. I just buzzed that out. There's no impedance between these two. What? I checked the resistor. The resistor's good. I checked the voltage here. Looks great. 3.3 volts. Alright. Something weird's happening. You guys see that alright? It should be. So the one thing that you're missing here, Tested, is we plopped in the old dev kit and it worked. Like, the circuit is functioning until we put this guy in there. I'm not sure if this is like a my probe's not great situation, or if this is a I have no idea. Are we actually not enabled right now? No, look at that! We've got 3.3 volts. We come here and check the resistor on the other side of the trace. Nothing. I can hear it wanting to. We could just hard tie it on. I might do that. I might add a little toggle switch to just pull on that pin up to 5 volts. Let's do it. Let's do it. Alright, so where's 5 volts on this guy? Maybe it just needs a little more base drive. Maybe that's just the long, short, and skinny of it. Alright. Just quick double check the pin out before I go and hard tie this. We want to check resistance. Back to this resistor. 0 ohms. Perfect. It could be a pin mapping thing too, like if I have this thing set to an output, but weak drive instead of strong drive, or something like that. I don't know. Could be a lot of things. VDD, boom. Permanent Gate drive enable. I want to see something happen. Sounds like a short on that side, but it was working. I know, right? Yeah. Well, honestly, if this works, I mean, we don't really need this micro to be compatible with the old design. We're basically ripping up and replacing everything about this design. The push-pull converter is being replaced with a full bridge. The inverter FETs are changing, and so is the output filter. The feedback stage is changing. Everything about this design is changing. So, like, all I want to do is see a sine wave. All I want to do is validate that the signals are flowing and kind of gawk at the fact that we're making 120 volts. So, I mean, we could try a bigger resistor, but I'll be content if we just get it working. That's alright with you guys. Yeah. I just want to have fun. Alright, here we go. Boost FETs permanently on. Let's see what we can do. You gotta be kidding me. You gotta be kidding me. What in the world? Literally? What? Let's just make sure it's hooked up right. I might have missed on the enable. It is possible. Okay. Let's check the voltage. Present. Get the resistor. There we go. This guy. Voltage on that pin should be 5 volts. Voltage on the enable should be 0. Permanently enabled. Great. Voltage on this enable resistor. I think I missed. I think it's 139. Cool. Looks good. Click it on. Check. Alright, we are no longer there. That looks great. So why is the high voltage rail not turning on now? I swear, it just doesn't want to work. It just doesn't want to cooperate. R14. It's just being a pest. Alright, checking the boost schematic again. R14 comes in, R35 is what we're looking for. R35. We're seeing 0.6 volts across it. Click enable. Click enable. We're still getting voltage across it. I think I missed. We're on the wrong pin. We're on the wrong pin. Easy to fix. Or is it that this actual pin isn't making good contact with the board? Could it just be that this pin isn't, because I took out the wire jumper. Yeah, I can shrink the scope a little. Yeah. Alright. So we're on the right pin. So if I just take that out, put this in, and use our jumper hook, I wonder if it'll turn on. I wonder if that's all it was this whole time, is that this crimp pin sucks. Okay, let's try it again, see if she turns on. Alright, switch to picture-in-picture again. Click 1 for arm, click 2 for go. What? The fan ramped up. That means we're pulling more power. Alright, I'll be quick. That's still enabled. This is enabled. We've enabled the boost. I don't know, tested. Maybe this needs a higher V in high. Maybe it's as simple as that. Our gate drivers need more voltage. I think that might be it, because we're enabling all the rails now. Wait a minute. That might have been working. Wait a minute. I think that might have been working. I think it is. I think it is actually working. But the problem is that our control loop is getting a really high voltage, so it's setting the PWM to the minimum value. Alright. So we could either set it to run open loop, which I don't have a jumper for, I need to reprogram. Or we just tie the analog feedback pin to ground. No worries. Hey. She's going. She's doing something. She's making a sine wave, I think. It's hard to tell, because I zoomed out. Hey! She's making a sine wave! Yeah! Sweet! Looks like we're not getting 120 volts. But that's cool. That sine wave looks a lot cleaner. Oh my goodness. Look at what happens when you actually run your control loop at the right sampling interval. Ooh, baby, that's a clean sine wave. And there's a couple glitches here and there, but that's a lot less than the old one. I like this DSP. I wish we could do a side-by-side comparison of the old one versus the new one, but I mean, the people that were here, yeah, that's what I call a pure sine wave output. Even through the bridges, oh yeah. I think those glitches are issues with the PWM where we interrupt a PWM cycle, where I'm not always catching it right, where I'm updating the value when I shouldn't be. But it could also be lag in the processor if one of my ISRs is taking a while. Oh yeah. That looks pretty. Oh my goodness, THD on that is glorious. What's our output voltage? Let's do a measure all. What are we getting? We're getting, where's RMS? 53 volts. So I could, woo! Hang on, I gotta turn that off. Our output filter is smoking hot. It likes it even less now. Oh man, that's a pretty sine wave though. Yeah, absolutely. Oh yeah, save the output on the scope. Oh, thanks guys. Yeah, I wasn't able to finish porting the code over, but this was a great proof of concept, right? This tells me that it's actually running well. It's able to interface with the circuit. So once we update the design, well, once we finish doing the analysis for the new inverter daughter card, we should be able to get this thing running great with the PSoC 6. One of the things that I'm kind of nervous about with this is all of the PSoC 6s that I want to use are BGA parts. THD 2%, nice guess. Yeah, oh, is that actually on the scope? Did it give THD? We could do the FFT. Let's do an FFT of that, actually. I'll do an FFT before we call it. Is there all BGA parts? And soldering a BGA onto our board kind of scares me. Not sure. I think it was 0.5 millimeter. But it just, it's a lot harder to inspect the joints unless you have an X-ray machine. And I don't know about you guys, but I don't have an X-ray machine. So it's like, I can hot air reflow it, I can put flux under there, but the only way that I'll be able to verify is if I actually give myself test access, like out to pins and probe it all. You've got an X-ray machine at home for boards? That's awesome. Maybe I'll just ship my protos over to you. You can scoot them through the X-ray and let me know if I've got any cracked solder balls under there. But, yeah. Holy crap. That's a control loop running on a PSoC 6. That's fun. At risk of blowing up the entire inverter stage, I think you guys watched the video where we blew up our old inverter stage with this thing. What could possibly go wrong? Let's hook it up and see if we can boost our output voltage up to... If we do the 2-to-1 scale... input voltage selector 110, and we'll just need to hook it up to the 220 volt output, and we should have 120 RMS. Rather than actually tweaking the code and making you guys wait 30 minutes, let's just use the scaler. What's this say? Nah, no need for X-ray. More of that 0.8 millimeter and 1 millimeter balls fine. 0.5 millimeter balls bad. Okay. So you think I could get away with a wider pitch BGA? I mean, it makes it easier to break out too. Everything's easier than that. Oh my goodness, that is a tight mains cord. There it is. Had it plugged in. Yeah. So I'll probably need to check the output voltage on this guy. Let's get the FFT set up. Oh goodness. Where's my math channel? Math channel. Channel 1. We want FFT operation on. We'll turn off our measure all. So now we should have an FFT. Should have an FFT. Dental X-ray machines, less than 1.5K. Oh, do it, man. Do it. DIY fluoroscope. Throw it up on your channel too. Either way, share it. Share it. However you can. Oh, you can't see the. Where can I get my meter so you guys can see it? There's a good spot. Let's kick on the output. So got the sine wave, as you can see. Let's scale our math channel. Wow, that's pretty good. You can see our 60 hertz peak. And not much else. THD on that is pretty good. Wow. On the output here, we're getting 100 volts out. 100 volts out. That's better than the 60. Cool. What do you guys think? Plug a light bulb in? Pull some power through it? I think we're technically running open loop right now, so I expect our output voltage to sag quite a bit. Yeah, it did. But we're running open loop. Can't really blame it. Fun. Fun. I'm a big fan. Just for giggles, I need to grab a. What is it? A USB stick. So you can save off that scope capture. So organized. Of course, I have one right here. Maybe. Hopefully. Oh boy. What? There's not just a bunch of crap off camera. What? This shop is organized, I swear. Alright. Hopefully somewhere. Not seeing SD cards. Empty. Flash drives, empty. Well, that's a shame. Good thing we've got a scope on it. I'll take a screenshot later. Okay, so the FFT range. We are going. Wow, that is hard to read. We're doing 100 hertz per division horizontally, and 10 dB volts in the vertical axis. So we're plotting from 0 to 1, 2, 3, 4, 5, 6, 7, 800 hertz. So we're capturing the first harmonics. If I scale this, now we're doing 1 kilohertz per division. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, almost up to a megahertz now. Yeah, so oh yeah, that's a good point. To get the hundreds of kilohertz. Let's do that. 10 kilohertz per division. Now we need to get up to 100 kilohertz per division. So now we should be able to see all kinds of garbage coming out. So yeah, what I want to do is I want to run this. We'll capture the screenshot, and then we'll switch back to the old controller and compare. Oh my. So when we're zoomed to the scale that lets us see those higher harmonics, we don't get very much of the waveform. That's kinda not great. Yeah, we've got to at least zoom out to there before we can really see it. That looks pretty weird. That looks goofy. It just looks like there's glitches every now and again, and it hoses it up. Like we don't have enough periods to get a good FFT. Yeah. That's where the spectrum starts getting weird. Up to there. You can see whenever there's a bunch of those glitches in frame, the noise floor kind of just... Which, that seems okay. That seems about right. But we might need a more advanced scope with a higher sample rate to get the higher frequency harmonics out of this thing. Yeah. Yeah. Maybe I'll have to actually do the upgrade hack on the DS1054 to, I think it has some ways to expand either the memory or the sample rate, or maybe both. That might give us better FFT range. But at any rate, I'll just zoom into this level. We're back to the 100 hertz per division. It seems we get a fair number of samples in there. Okay, that's kind of what we got for the spectrum. If we disable, unplug, swap the old micro back in. Oh my goodness, that's in there tight. Oh yeah. Cool stuff. Oh, that feels good. It feels good to see something like that work. I think it was just the janky pins. I think that's all the problem was. I think it was just the cheap Amazon pins. It's not terribly surprising. It is a little disappointing. Oh. Okay. Can we up the vertical scale? Sure thing. Yeah, we can up the vertical scale. Maximize our 8 bits. Grab the old inverter controller. Pull her over. Let's get her fired up again. And we'll maximize our 8 bits. I'm expecting the waveform, I mean, I still tried to make it work, I just didn't have much oomph. I think the spectrum will be a little dirtier. I don't know about you guys. That noise floor, I'm seeing a lot more harmonics showing up in this spectrum. See all those harmonics? Those other peaks we're getting? Yeah, I think the new micro is good news. Let's see what I can do with regards to maximizing the bits. Yeah, you can definitely see those other peaks. We start to clip on the resolution here, but you can definitely see those other peaks coming out of the FFT. Or we can maximize this guy. But come on now. There it is. I'm liking this PSoC 6, guys. I think we're gonna have a nice, clean inverter output. Yeah. I'm excited. So I'll get this thing pulled off the bench real quick, and we'll close this one out. I'll just talk a little bit about the difference between the old micro and the new micro, and kind of why this is a change. Because obviously, it's a lot of work to change what micro you're gonna use. It's a lot of work. You gotta like port all your code and deal with assembling your circuits a different way. There's a lot of change. There's a lot of churn, but I really think it's going to be worthwhile for our UPS. Oh goodness. Oh boy. Oh. Yeah, I'm really excited about this change. So basically we're going from our old dev kit, which we ended up just putting the header right on the board and dropping the daughter card on. We're going from this dev kit to this one. Never mind our napkin math on this old dev kit. We were working on the larger storage rack, the larger organizer, and I needed to work down some measurements, and I was cutting the extrusion. Anyways, so we've got the PSoC 4 dev kit and the PSoC 6 dev kit, and the critical difference, the reason why I chose PSoC 6 is because, one, I'm really happy. I don't, if you guys aren't familiar with this product series, what it is essentially an FPGA married to a micro. It's a very limited FPGA. It doesn't have a whole lot of gates, but it lets you reconfigure the way the IC works. If you want to remap pins, you can remap pins. If you want to invert a PWM output or not invert it, you can change it both ways. Upgrade hack might be worthwhile. I think it's on the yeah, totally. I'm pretty sure you like put in a USB key with like an upgrade thing or hook it up in the Ethernet port in the back. I can look into it. It was pretty straightforward. I just had to carve out some time and do it. Yep. Yeah. Yep. Absolutely. I was looking at how to get the like a raw image out. I don't know if there's a good way to get the live feed directly out, but that would certainly be higher quality. Maybe that's an upgrade thing too. I'll look into that. I didn't see a way other than actually like hacking the display interface, but I'll take a look. But so there were a couple things about the PSoC 4. There are versions of the PSoC 4 family that have a floating point unit, hardware floating point accelerator. This does not have it. The PSoC 6 does. That's one of the main things between these two. The other thing is that this guy's running at like 4 times, 5 times the clock frequency of the old IC. So we've got a floating point math accelerator, higher clock speed, and just a more modern feature set. The ADC is definitely improved in this thing. It's yeah, I know. I'd love to get display data out of this. There's a Hackaday project that has driverless Rigol screen capture over LAN. Yeah. Might have to look into that. The PC I'm using does have 2 LAN interfaces, so I could designate. Oh, you're telling me, Test, that if I get display data straight out of the scope, that means I don't have to have 2 cameras sitting on this bench that I'm tripping over. I'd love to do that. All right, I'll have to do that. I'm sure I could get that bolted into OBS. That will be awesome. I'll take that as an action. Hackaday, driverless, screen capture over LAN. Wow. Can I love that comment? I want to love that comment. Nope. All I can do is hide you, put you in a timeout, or oh wow, I can make you guys moderators? Dude, I'd consider that. Yeah, cool. I'll have to look at that Hackaday project. So yeah, basically it's the floating point unit, the higher clock speed. This thing's got like a ton of prescalers in there for the PLL. So there's basically a dedicated PLL for every single peripheral in this micro. So I can really fine tune the speed of every single peripheral, where all of the peripherals on the PSoC 4 are locked to the same peripheral clock, and that's very limiting. So basically I've got designated PLLs that are running the control loop at a very exact frequency, that are running the PWM generation at a very precise frequency, and that are running the ADC at a very precise polling frequency. And all of that together means that this micro's THD is way less, because the timing of all the processing, the timing of all the sampling is like right there, right? We're talking ppm, whatever the tolerance of your crystal is, that's what you're getting out of your PLL. So, you know, if we put like a hardware digital oscillator that's very well characterized and has very tight tolerance on frequency, we can get, you know, 60 hertz out of this thing that is 60.000 hertz. Tested, were you talking about the display data out of the scope with the tell you how to do it? I'm not sure. I'll look into it. I'll let you know when I know. By the way, yeah, so the just finishing this thing out. Definitely check these out if they aren't gone already. I'd be happy to ship them wherever. Yep. And yeah. Oh, that's what I wanted to say. Next week, no stream next week. Sad day, but we've got a lot going on with the temperature monitor and the UPS. We got a lot of stuff to get done, so I'm gonna take this time next week and work a little bit on some of that. Maybe relax a little, have an extra cup of coffee. I don't know, but it's been an awesome run. It's been an awesome few weeks where we've had this time to share in the shop together. Definitely going to come back and do more streams with you guys when we get more prototypes in. So it'll be a pretty long series of videos as we bring up the inverter daughter card, battery charger. Yeah, man, I'm glad you love the streams, No Carb. I love them too. It's definitely a highlight of my week. Just to get in here, mess around in the shop with you guys live. I love the Q&A. You guys have encouraged me to get new equipment, and hopefully we get a great screen capture for next time. Whew. I think, I don't want to commit, but I think that I might be able to get this up to 1080 next time. I think I'll be able to make a graphics card change that'll bump up our resolution. That should be an awesome upgrade to the streaming setup. So, yep. When it makes sense, when we've got something cool to talk about and stream live, yeah, we'll definitely get in and just do it the same way, right? So I'll change the stream so it's got the upcoming dates. You guys have a couple days notice, and we'll hang out again. It'll still be Saturdays when it happens. Saturdays, 8:30, same time. Just not next week. We're gonna take a couple weeks off and dive into some of these projects. Yikes! Is this coming through in 480p? Is that my fault? Is that all you guys get? Oh my goodness. Oh, wait a minute. It says I can bump it up to 720 or 1080. Look at that. Is your internet not too great over there? Or maybe it's getting the stream through. Well, at any rate, we'll get it to crispier 1080p. The bitrate's pretty low right now, but we'll get the quality up. Oh yeah, no worries, guys. I think it's been what, a month, 2 months? We've had these for quite a while. But before that, there's probably 6 months and 8-month hiatus. I mean, I don't want anything like that. So we'll take a couple weeks off. We'll come back in and we'll have to bring up the Project Seth. That board, we'll have to do the final assembly with the through-hole parts, do a PCBA inspection. Internet in Australia is still pretty bad, but it's more small screen, etc. Not sure why. Maybe latency and stuff. Yeah, it's weird. It's bouncing back to me pretty well, but that's probably not very hard. It probably just goes to one node and bounces right back. But it claims you guys can get 1080, so we'll see. But I'll miss this too. So we'll make it a priority to come back and stream again soon. Another thought that I had in the interim, if we don't have a lot to stream, there's apparently this feature on YouTube called Premieres where we can release a video and like hang out and chat with you guys in real time while we watch it. That could be fun as a way that we can keep some of this real-time engagement going when we can't stream. So let me know if you'd be interested in that too. I'd be open to it. Just need to maybe tweak the release schedule so that I can actually be here and watch with you guys. But yeah, that's what's going on. We got the PSoC 6. Gotta finish doing it up. See you guys soon. Thank you as always for watching. I hope you guys learned something. No Corp says I have the 720p list, but it's loaded 480p. Couldn't tell ya. A break in schedule is fine. Yeah, the algorithm definitely likes consistency, for sure. But they're making all kinds of tweaks, and I don't know. I think we just gotta do what's right. Algorithm's gonna do what it's gonna do. Who knows? But as long as we're here, as long as we're having a good time, yeah, that's all I need. So yeah, thank you guys for watching. Hope you enjoyed or learned something or had a good laugh with us. We'll talk to you again soon. Take care. Thanks for watching. Bye.